Hello and welcome to Vodcast 12.2. In this vodcast, we will overview humidity. Put as simply as possible, humidity is the amount of water vapor in the air. Now, another very important term I want to introduce is saturated air. Air is saturated if it is absolutely filled to capacity with water vapor. An analogy I like to use is a football game being held in a very large stadium, say Memorial Stadium, the home of the Fighting Illini. If the seating capacity in Memorial Stadium is roughly 60,000, we would consider the stadium quote-unquote saturated if there were 60,000 fans watching that game. Anything less than full capacity would be unsaturated. Now, when we consider the air, it gets a little bit more complicated because saturation is temperature dependent. Note that as the temperature increases, the air is capable of holding more water vapor. As a specific example, let's look at the temperature of 41 degrees Fahrenheit. If we have 1 kilogram of air that is at 41 degrees Fahrenheit, it can hold 5 grams of water vapor. But if we now take that same air sample at 41 degrees Fahrenheit and warm it to 50 degrees Fahrenheit, the air can now hold 7 grams of water vapor. Another very important thing to realize when you take a look at this image is that for every 18 degree Fahrenheit jump in temperature, the air is capable of holding twice as much water vapor. As an example, 1 kilogram of air at 50 degrees Fahrenheit can hold 7 grams of water vapor, but if we increase the air temperature by 18 degrees, so the air is now 68 degrees Fahrenheit, the air is now capable of holding 14 grams of water vapor. But one of the key concepts you see when considering this graph is that warm air has a much greater capacity for water vapor than cold air. In other words, as the temperature increases, air is capable of holding more water vapor. One last thing I'd like to point out, because it's going to be very helpful in the coming slides, is that by increasing the temperature of the air, it's capable of holding more water vapor. But if you decrease the temperature of the air will need less water vapor in it to reach saturation. Let's talk about how we measure humidity. One common way to measure humidity, and a lot of weather apps and meteorologists will reference this particular way of measuring humidity, is relative humidity. Relative humidity will be expressed as a percent. And if the air is saturated for a given temperature, the percentage will be 100%. Let me go back to my football game being held at a large stadium analogy. If the stadium capacity is 60,000 and there are 60,000 fans in attendance, the stadium is 100% filled. It's a sold out crowd. However, if there are only 30,000 fans in the stadium would be 50% full. Well, when we're talking about relative humidity, it's the exact same idea. At a specific temperature, the air is capable of holding a specific amount of water vapor when that air is saturated. But I think it's important that we state that relative humidity can be changed by changing the air temperature. I'd like to go back to my sporting example just one more time. Let's suppose there are 30,000 fans in Memorial Stadium, and its capacity is 60,000. Well, if you take 30,000 and divide by 60,000 and then multiply by 100, you would find that the stadium is 50% full. But let's suppose the athletic director doesn't like that. He doesn't like the fact that on TV his stadium only looks half full. So he decides to remove 20,000 seats from the stadium. Now, by removing 20,000 seats, the new capacity is only 40,000. And if 30,000 fans are in that stadium, it would now be 75% full. It's the exact same idea with relative humidity. If I can put back up the graph from the previous slide, let's pretend that the air temperature is 68 degrees Fahrenheit, and in 1 kilogram of air, there are 7 grams of water vapor. At 68 degrees Fahrenheit, 1 kilogram of air is capable of holding 14 grams of water vapor at saturation. So the relative humidity would be 50%. But let's suppose the temperature drops from 68 degrees Fahrenheit to 50 degrees Fahrenheit. At 50 degrees Fahrenheit, that 1 kilogram of air is only capable of holding 7 grams of water vapor at saturation. And if there's still 7 grams of water vapor in the air now that it's cooled down to 50 degrees Fahrenheit, the relative humidity would have increased from 50% to 100%. The graph shown in the middle of this slide is extremely important, and it kind of highlights exactly what I just talked about. The lowest relative humidity will typically occur in the middle afternoon because that's when the air temperature is the highest. And remember, high temperature air is capable of holding a lot of water vapor, but as that air cools down, it's not capable of holding as much water vapor. So the highest relative humidity will often occur in the early morning hours when the temperature is the lowest. What often happens is the air is cooled to a point that it can no longer hold all the water vapor in it, and some of that water vapor will settle out onto grass or onto your car window or just about any other surface that it can grab onto. And the last thing I like to point out is the frosty beer mug you see over at the far right of this slide. Obviously, I'm not advocating drinking, but those water droplets you see forming on the side of the mug are there because the mug is extremely cold. So the quote-unquote sweating of that mug is literally water vapor condensating on its cool surface. Okay, at this point I'd like to take a quantitative view of relative humidity. If we reference the table shown on the very first slide, when the air temperature is 25 degrees Celsius, which is about 77 degrees Fahrenheit, the water vapor content at saturation will be 20 grams. So if there are only 10 grams of water vapor in the flask, and saturated air at 25 degrees Celsius will contain 20 grams of water vapor, the relative humidity is 10 grams of water vapor divided by 20 grams of water vapor multiplied by 100, and that's 50%. Now in part B, we're going to cool the flask down to 15 degrees Celsius, which is a temperature of 59 degrees Fahrenheit. Saturated air at 59 degrees Fahrenheit will contain 10 grams of water vapor. And if there were 10 grams of water vapor in the flask, then our new relative humidity would be 100%. To explain, air at 15 degrees Celsius is capable of holding 10 grams of water vapor, and we had 10 grams of water vapor in the flask, so 10 divided by 10 is 1. 1 times 100 would give you a 100% relative humidity. We would say that the air in the flask in part B is saturated. Okay, now in part C, things get interesting. We're going to cool the air down to 5 degrees Celsius, and that corresponds to a somewhat chilly temperature of 41 degrees Fahrenheit. At 41 degrees Fahrenheit, 1 kilogram of saturated air would only contain 5 grams of water vapor. Well, we have a problem because we originally had 10 grams of water vapor in our flask. So what basically happens is the air will be saturated, and at 41 degrees Fahrenheit, saturated air would contain 5 grams of water vapor. But the other 5 grams of water that were originally in the flask don't just magically disappear. The other 5 grams will have condensated. In fact, those 5 grams of liquid water that are now in the flask could be the dew that you would find on the grass in the morning. And for the record, those 5 grams of liquid water could also form clouds or fog. Our other means of measuring humidity is what's known as dew point temperature. And if you watch the news, meteorologists will very often mention this particular measurement. Put as simply as possible, dew point temperature is the temperature to which a parcel of air would need to be cooled to reach saturation. In the images that we just looked at, the dew point temperature would have been 15 degrees Celsius. In other words, that was the temperature in which we had 100% relative humidity. Now, typically speaking, a high dew point temperature means that there is a lot of water vapor in the air. Generally speaking, the higher the dew point temperature, the muggier the day will be. Now here's another very important fact about dew point temperature. For every 18 degrees Fahrenheit increase in dew point temperature, the air will contain about double the amount of water vapor. As an example, let's take a look at this map shown on this image. If you're in Miami, Florida, where let's say the dew point temperature is 70 degrees Fahrenheit, you would find double the amount of water vapor in the air than you would in Chicago, where the dew point temperature would be approximately, say, 52 degrees Fahrenheit. Generally speaking, your high dew point temperatures in the United States will typically occur in the southeast United States, and your lower dew point temperatures will tend to occur out west, which is the drier part of our country. Long story short, high dew point temperatures mean extremely moist air, whereas low dew point temperatures will correspond to dry air. Okay, our final consideration in this vodcast is going to be you doing a little bit of problem solving. Shown is a picture of a house, and we see what looks like smoke coming out of the chimney. But that's actually not smoke, it's water. I want you to pause the video and try to answer this question and explain your answer. Is the relative humidity higher inside or outside of the house? To answer the question, the humidity inside the house will be less than the humidity outside the house. Well, for starters, it's important that you understand that what you see coming out of that chimney is essentially a cloud. The water vapor in the air is undergoing condensation when it interacts with the outside air. Now, for that condensation to occur once the water vapor in the air gets outside the chimney, the air must reach its dew point. Because remember, the dew point is the temperature in which water vapor begins to condense. Knowing that's the case, we can reason that the air inside the house was unsaturated or above the dew point. So the key idea here is that warm air can hold much more water vapor than cold air. So that warm air would have a lower relative humidity than the outside air. If the temperature inside the house is warm, and there's a certain amount of water vapor in the air, but it's less than the level needed for saturation, then the way to get that water vapor to condense would be to decrease the temperature of the air. In this image, that decrease in temperature occurs once that air gets out of the chimney into the colder surrounding air. Okay, I hope that explanation made sense, and at this point, that is the conclusion of this vodcast. In our next video, we will talk about adiabatic heating and cooling. And then from there, we'll talk about processes that lift air, and then we'll get into cloud formation.